Hello everyone, welcome to lecture number 55 of this NPTEL course in Riemannian geometry. So in the next few lectures I will try to characterize all complete Riemannian manifolds whose sectional curvature is identically constant. Okay, so before that let me remind you of the following notation. So for kappa in R, so any real number, we set M kappa G kappa to be the following model spaces. So it is the sphere of radius 1 by square root of kappa with the corresponding round metric if kappa is positive. It is the usual Euclidean space Rn Grn if kappa is 0, and it is a hyperbolic space of radius 1 by minus square root 1 by square root of minus kappa. So these are Mn k I mean M kappa of dimension k if kappa is negative. Okay. So note that the sectional curvature of G kappa is then identically equal to kappa, which just means that for all points P in M kappa and for all two planes in the tangent space at that point, so all two dimensional planes in the tangent space at that point, we basically have that the sectional curvature of the tangent plane is actually equal to kappa. Okay. So such manifolds are examples of what are called as space forms. So that is my next definition. So a space form is a complete Riemannian manifold whose sectional curvature is identically equal to kappa. That again just means this, that for all points and for all two planes the sectional curvature is kappa. Okay, so let me also remind you of maybe what the definition of the sectional curvature was, since it has been a long time. So so remember that suppose pi is spanned by these vectors x and y, then the sectional curvature of pi was basically Rm of x comma y comma x divided by this. Okay, and in fact this denominator here is basically the norm squared of x wedge y. Okay. So sometimes it will be convenient to use the following notation. We will denote this plane as also x wedge y. This is not quite accurate because if you for instance scale x or y, the wedge product will scale accordingly, but the point is that they will still span the same plane. Okay. So this is purely a notational convenience. Okay. So sometimes we denote pi by this. So this is not on the nose, this is not quite correct, but this is a convenient notation to use sometimes. Alright, so here is the main theorem that we would like to prove in the next few lectures. So this is called the uniformization of space forms. Okay. So let Mg be a simply connected space form if you remember, that just means that the fundamental group is trivial with, let us say, the sectional curvature, that is a constant because it is a space form. Let us assume that the constant is given by this kappa. Okay. Then the claim is that Mg is actually isometric to the corresponding model space. Okay. So why is this called the uniformization theorem? That is because if you remember uniformization theorem from sort of Riemann surfaces, that basically just says that any simply connected Riemann surface is one of three models, either it's the Riemann sphere or the unit disk, or it's C, right. So this is the analog for Riemannian manifolds for space forms. Okay. So it will take about 3 or 4 lectures to actually prove this. I want to state an immediate corollary which I will prove also right away. So this is the characterization. I mean, you might wonder what happens if it is not simply connected, right. There might be space forms which are not simply connected. For instance, you can think of the flat torus, right, that has 0 curvature, but it is clearly not simply connected, right. So what happens in that case? So in the case of flat torus, we know that even though it is not simply connected, you can actually write it as a quotient of the corresponding model space, which is the Euclidean space in that case, modulo some action of some lattice, right. So it turns out that that is actually true in more generality. So that is what the next corollary is about. So let Mg be a space form such that the sectional curvature is identically kappa, then there exists a discrete subgroup in the isometry group of the model space. So let me write it a bit more clearly. So gamma is in the isometry group of the model space. So here the topology on the isometry group is the usual compact open topology. So it is discrete in the compact open topology such that Mg is actually isometric to the quotient of the model space. Okay. And in fact, this gamma is nothing but the fundamental group of M. Okay. So let me quickly prove this, assuming of course the uniformization theorem. So let M tilde M mu be the universal cover of M. Okay. And we define G tilde to be simply the pullback. So you because it is the universal cover, it is a cover, so it is a local diffeomorphism. So you can pull back the metric on M to define a Riemannian metric on M tilde, and then the sectional curvature is identically kappa, and M tilde is simply connected. one can also show that this is actually also complete. Okay. So then by the uniformization, this implies that that m tilde g tilde is isometric to the corresponding model space. Okay. And so then by from general covering space theory, this is something that I reviewed a few lectures back. So by the general covering space theory, we know that that M is basically m tilde modded out by the fundamental group. Okay. All right. So so this of course you can, I mean by the uniformization theorem, this is basically so you can think of the fundamental group not only acting on m tilde, but because m tilde is diffeomorphic to m kappa, you can think of it as acting on m kappa. So the first claim is that the fundamental group actually acts by isometries. Okay. What is the proof of this? So let us take an element in the fundamental group, then you have basically the following picture. So remember the action of the I mean this defines a diffeomorphism of the universal cover, and that is basically just by using this path lifting property, right. So we went over this when during our discussion of covering spaces. So you have the following picture, right, which commutes. So you basically have mu composed with the map defined by alpha, that is the same as mu. Okay. But then if you take the pullback of g tilde under this map, well, what is g tilde? G tilde is precisely the pullback of g under mu, but that is just going to be the pullback of this composition, which by this the commutativity of this diagram is just mu star g, but mu star g is by definition g tilde. So this shows that that this is actually an isometry. Okay. All right. The second claim is that this is in fact a discrete subgroup. So so pi 1 of m is a discrete subset in the isometry group. Okay. So what is the proof of this? Well, suppose there exists a sequence, an infinite sequence with a limit point, right. So if it is discrete, it cannot have a limit point. So let us say it does have a limit point, then we get some sort of a contradiction. So let us say it has a limit point in the isometry group. Then this implies that for all p tilde in m tilde, if you look at the corresponding points which are the map of p tilde under the diffeomorphism corresponding to alpha I, then this has a limit point. Okay, now in m tilde, yeah. Okay, but if you take the image of each of these points under mu, well, that's basically just mu of p tilde. Okay, so that's fixed, which is p. But we have already seen that the inverse image of p is a discrete set, so it cannot have a limit point. So this is some comment that I had made right after the definition of covering spaces, right? And the point is that, I mean, because of this local diffeomorphism property, it follows easily that this is a discrete set, but that's a contradiction, because we are saying that it actually has there's a limit point in that set, but that set ought to be discrete, so that's a contradiction. Okay. Alright, so this basically proves the corollary that the upshot is that Mg is actually isometric to the model space, the quotient of the model space by a discrete subgroup of the isometry group, and in fact the proof shows that this discrete subgroup is actually just the fundamental group of M. It's isomorphic to the fundamental group of M. Okay. Alright, so this proves the corollary. So in order to prove the uniformization theorem, we will have to do some calculations in polar coordinates. So we will have to use Jacobi fields to characterize, firstly I mean in order to show that you have an isometry with the model space, one first actually shows that you have a local isometry in any geodesic normal neighborhood. Okay. So any space form, if you take any geodesic normal neighborhood, then that is isometric to a corresponding neighborhood in the model space, and then one uses some global arguments like this Ambrose theorem, etc., to go from the local isometry to a global isometry. So in order to prove this local isometry result, we really need to understand what the model spaces look like in polar coordinates, right. So the next thing I want to talk about in this lecture is basically the model space metric in polar coordinates. Okay, so before I state the main result, let me make a definition that will be very useful throughout the rest of the course. So we define the generalized sine function by so it depends on this kappa, sine kappa of t, that is equal to 1 by square root of kappa, the usual trigonometric sine function square root of kappa times t. This is if kappa is positive, it is equal to t if kappa is 0, and it is equal to this factor times the hyperbolic sine if kappa is negative. Okay. Right, so let me just remind you, so recall that the hyperbolic sine function applied to some x is basically just e to the x minus e to the minus x by 2. Okay. All right, so also an important remark will be that so this is basically the unique solution to the following second order ordinary differential equation, namely u double prime plus kappa u is 0, and with the initial conditions that u of 0 is 0, u prime of 0 is 1. Okay. So, the unique solution to this second order linear ODE is precisely given by this generalized sine function. Okay. Right. So, here is the main proposition that I want to establish. So, let O kappa be some fixed point in M kappa, okay, and let Rk be the so be the distance function, right. Distance function in this model space. Okay. Also, if K is positive, so that means we are looking at really a round sphere, we let minus OK denote the antipodal point. So, for instance, one can just take OK to be the north pole, and then minus OK is basically going to be the south pole. Okay. And then we let u kappa basically be M kappa minus this antipodal point if K is positive, and it is all of M kappa if K is non-positive. Then there exists geodesic normal coordinates centered at OK on all of UK. So, for instance, if you are dealing with Euclidean space or the hyperbolic space, then you actually have global geodesic normal coordinates, which of course follows from the Cartan-Hadamard theorem, right, because the exponential map is a diffeomorphism. Okay. On the other hand, if you are working with the sphere, then you basically have so maybe I will draw a picture, but you only have geodesic normal coordinates. Let us say you are looking at the north pole as the center, then you have geodesic normal coordinates on the entire sphere except at the south pole. Okay. And furthermore, this is the key point, I have the following polar coordinate expression of the metric. So, restricted to this geodesic normal coordinate, this looks like d Rk squared plus this generalized sine function applied to R kappa times the metric on the sphere. So, where R kappa is the distance from O kappa, but in terms of these normal coordinates is basically just the Euclidean distance, and G Sn minus 1 is the usual round metric on the unit sphere in these coordinates. So, in other words, let me explain what is happening. So remark, let me maybe elaborate on what is happening. So, the idea is that you take the unit tangent sphere at that point, then at the point OK in the geodesic normal coordinates, the metric basically is exactly Euclidean. So, one can identify this with Sn minus 1. Okay. and for any point, so then one basically has this map from 0 to T kappa. I will explain what T kappa is, cross this to all of uk, where you basically take r comma theta and this goes to the point exponential at ok of r theta. Okay. These are exactly, I mean right, and so then I am saying that you identify this with Sn minus 1 with the usual sort of round metric. One can do that because at the point ok the metric G is basically the Euclidean metric, right. So then all I am saying is that if you pull back your Riemannian metric on uk, then in these coordinates it will basically take this form. Okay, that is really the meaning of the proposition. Yeah. And what is Tk? Well, Tk is basically pi by square root of kappa if kappa is positive and is infinity if kappa is non-positive. So again, why do we need this this time? That is because if you look at the sphere and the tangent space, then there is this ball in the tangent space of radius pi by root k. The exponential map is basically a diffeomorphism on that ball of radius pi by root k in the tangent space, and it covers the entire sphere except the south pole. Okay. Right. Okay, so this is what the statement means. So let me maybe sort of quickly give a proof. So this will I mean this will be a slightly longer lecture, but so my apologies for that. So let us first do the Euclidean case. So let kappa be equal to 0. So i.e. my model space that I am looking at is basically just the Euclidean space. Okay. So as before, we consider the following map phi. So this is the polar coordinate map, which is smooth everywhere except so maybe even in the previous slide I should have said that this is a diffeo everywhere except at the point ok. Okay. Similarly here the polar coordinates give you a coordinate system on all of Rn except at the origin. Okay, so so the map is that r comma theta simply goes to r theta, right. So you have a unit vector here, you just scale that unit vector by this radial coordinate. So now in order to I mean what is our goal? Our goal is to compute the pullback of the Euclidean metric in these coordinates, right. So in order to do that we have to understand what the derivative of phi looks like. So there are basically two two things one needs to do: compute d phi of the radial directions and compute d phi of x, where x is tangential to the sphere, right. So let's compute d phi of del r. Okay, let's say at a point r comma theta. Okay. Then by definition this is basically you just take a path in the radial coordinate. So this is d by dt at t equals 0, phi applied to a trivial path in the radial coordinate is just r plus t times theta. So that is going to be d by dt at t equals 0 of r plus t times theta, which is of course just theta. Okay. So the derivative map takes the radial vector. So the idea is that right, it takes the radial vector to to this theta. Okay. So let me draw a picture. So let us say r theta is a point here, then the radial vector basically is mapped to this vector theta here. Okay. All right, let us compute the other derivative. So d phi of x. So again by definition, again at this point r theta, so this is d by dt at t equals 0 phi of r times gamma of t, where gamma of t is a curve on the sphere such that gamma of 0 is the point theta, gamma prime at 0 is this tangent vector x, right. But then that just implies that if you differentiate, this is just going to be r times the derivative at 0, which is x, right. Okay, so again in the picture you have the unit sphere here, you have some tangent vector x. So under the derivative map at this point it will correspond to the same tangent vector but scaled by the radial distance. Okay. So that is what the derivative map does. So now that we have the derivative map, one can easily now compute. So I will leave this as an exercise for you to check that phi star right. So phi star g of del r comma x is 0, phi star g of del r comma del r is basically just mod theta squared, which is 1. And this is basically the Euclidean norm of Rx, which is r times the Euclidean norm of x, right. So this implies that phi star g is equal to dr squared plus r squared times the round metric on a lower dimensional sphere. So this proves the proposition in the case of the Euclidean space. Now for spaces with the model spaces with positive and negative curvature, it all boils down to the simple observation that in either of those cases the metrics are actually conformal to the Euclidean metric. Okay, so let me work out the negative curvature case, and then I will leave the positive curvature case as an example, as an exercise. So it is more convenient to actually use the Poincare ball model rather than the hyperboloid. Okay. Also by rescaling, we may actually assume that kappa is equal to -1. Okay. So then what is the metric on the ball? So remember the Poincare ball metric, it is basically just 4 by 1 minus squared times the Euclidean metric. Okay. So that is basically equal to, so you put x mod x to be the Euclidean distance r. So this is just 4 by 1 minus r squared whole squared dr squared, because the Euclidean metric itself we have seen is dr squared plus r squared times the metric on the round sphere. So this is going to be 4r squared by 1 minus r squared whole squared, the metric on the round sphere. Okay. Now my goal is to rewrite this in terms of the radial distance in the ball metric. Okay. So so for that let me remind you of a calculation that we did a long time back when we introduced these metrics in the first place. So let us say you take a point x with Euclidean distance r, right. Then the distance in the hyperbolic in the Poincare ball metric, which we are denoting by r kappa, or here kappa is -1. So r -1, let me, this is not a very nice notation, so let me just put kappa. Well, that is if you go back to your notes from that lecture, this is precisely this, okay. So now solving for r, we basically get that r is e to the r e to the 2 r kappa minus 1 by okay. All right. So also one can differentiate this and differentiate rk and see that this is just 1 minus 2 by 1 minus r squared times dr, which means that dr kappa squared is basically 4 by 1 minus r squared dr squared, okay. So now if you go back, you see that this first term is then exactly dr kappa squared, and one can show that this is again a simple calculation, that the other term that shows up in front of g of the round sphere, so that is this term, is precisely the hyperbolic sine squared applied to r kappa, okay. So then that means that the ball metric in these new coordinates is basically just this, which is what I was claiming, right. Okay, one can do something similar with so maybe I'll just take 2 more minutes and maybe I'll just complete the proof also for kappa positive. So again, without loss of generality, we assume that kappa is +1 this time. So then the idea is that we use stereographic projection from the south pole, okay. So we take the stereographic projection from the south pole, okay. So let x1 xn be coordinates on Sn minus the south pole obtained by stereographic projection. From the south pole. Then in fact one can check that the round metric on the sphere restricted to the sphere minus the south pole in these stereographic projection coordinates is given precisely by this. So it actually has a very similar formula to the Poincare ball model, except you now have a plus sign in the denominator, okay. So again one can expand this in terms of the Euclidean metric and polar coordinates to just be this, okay. So now in these stereographic projections, I mean, what are the minimal geodesics on the sphere? They are basically great circles from the north pole, right. Okay, so so one can actually check that I mean, if you compute the length using this formula, then this is a nice exercise again that r kappa in this case is related by arctan to arctan of r. Okay. Then one can do something similar to what we did with the Poincare ball model. One can compute that drk squared is precisely 4 by 1 plus r squared whole squared dr squared. So this turns out to be precisely dr kappa squared. On the other hand, this guy is precisely sine squared. Is precisely the usual sine squared applied to r kappa. Okay. So then we are done with the proof of the proposition. Okay. So in the next lecture I am actually going to take an arbitrary space form and try to compute the metric and polar coordinates in a geodesic normal neighborhood, and then show that I will actually end up exactly with these formulae, which shows that which will show that at least locally any space form is isometric to these local neighborhoods in a model space. So that will be the first part of our proof of the uniformization theorem, and then we will have to do some global argument. Okay. Alright, so that is it for this lecture. Thank you for your attention, and I will see you next time around. Thanks.